This afternoon, we'll talk more about the Kinematics tool, reference frames, topologies of tectonic plates, rasters, time-dependent rasters, and so on. And tomorrow, we'll go into how you can import your own data. So whether it's your geochronology, whether it's your fossils, whether it's whatever you need, how to bring that in. We'll look at some of the 3D visualization, some of the Python API in case you wanted to process data more automatically. And then in the afternoon, we'll talk more about deforming plate reconstructions, how you can really get into the guts of editing the rotation file, which is what controls motions in GPlates. And then we'll have a little bit of a discussion on paleogeography, paleoprecipitation, and question and answer. So one of the things I'd ask you, if you can, if you think any of this is useful or interesting, is maybe come with your own idea of what you'd like to do in GPlates, and maybe I can give you some tips and hints on how to do that. So I won't dwell too much on this, but a couple of weeks ago, we talked about how geology and the things that we do in GPlates and elsewhere is really important for the sustainable development goals, for energy, for reducing poverty, for all of these materials. And this is a great poster I showed as well of the Geological Society of London, all these very relevant things that we all do in geosciences. Okay. So this is the GPlates export output, essentially, turned into an animation. And you can see that the model here is centered on Southeast Asia, on this part. It's a very important part of the world that links the Pacific and the Indian Ocean, tectonics, and of course the Indonesian through flow, which was constricted and closed in the last 25 million years, and the Southern Ocean was open instead. The biggest innovation that came with GPlates only in about 2010, 2011 is the development of this ability to actually track the plate boundaries. So hopefully everybody can see the pink lines, the subduction zones, and then the black lines represent mid-ocean ridges and transforms. And you can then interrogate this model numerically by extracting the velocities, extracting all sorts of other parameters, plate areas, plate speeds, and linking that to many other software codes, which we'll talk about in the next couple of days. Here's just an example of mantle convection that's being run using GPlates velocities on the surface. That can be used to understand the dynamic topography, so like what the broad scale topography on our planet in Southeast Asia and everywhere else, of course. And of course, for Southeast Asia, I think some of the people here are working on, Wallacea and biogeography and evolution. And of course, that is linked to tectonics as well. So many people who use our software, use GPlates and the model, they're actually in the evolutionary biology community. Okay, they're paleoclimate modelers. They're people in industry and people doing basic science research. We can take this much further back in time. I showed this a couple of weeks ago. We can try to understand how these terrains moved before Pangaea, the supercontinent. We'll talk a little bit about what kind of data we use to constrain that, like paleomagnetic data and other geological data as well. And I mentioned that we'll go through some of the deforming plate reconstructions. So some of you who might be interested in deformation of the crust, so rifting or convergence and collision, you can model, at least here, the crustal thickness changes through time, as well as tectonic subsidence and things like that in basins. And this is all part of the whole Earth modeling ecosystem that we're building in Sydney, from the mantle to the surface tectonics, but also the paleoclimate and landscape evolution models, right? So hopefully you're getting an idea of how we can use the plate tectonics to help us understand landscape evolution and even life on Earth for a very long period of time. And the key in all of this as well is that all of these tools, all the software is open source, community free software that you can use, your students can use. There are no limitations. You can take the software, you can modify the software, you can improve it yourself. It's totally open source and there are no restrictions to its use. Okay. Okay, so let's actually get started with a demonstration just so that you can get familiar and using GPlates very quickly. I'll have some more slides to show throughout. We'll break it up a little bit. But when you open GPlates, you get this very boring gray screen. Okay, there's nothing here. But it's actually very quick and easy to get started. Okay, first option is to just go into the data bundle that I gave you. Make sure that you've unzipped that folder, right? GPlates cannot see inside zipped, compressed folders. Okay, and then if you go into this folder called Zahirovic et al. 2022, you'll see a bunch of files in here. Okay. Okay, I hope everyone has managed to find some files. Great. Okay. While we're here, I wanted to also describe what kind of files GPlates works with, just to give you a sense of what to expect later. So one of the files is this .rot file. Okay, it's a rotation file, and I can open it in a simple text editor. Let me text. Oops, that's not the file, but that's okay. So here is what the rotation file looks like. And later on today, we'll talk about what these columns mean, what these numbers mean. Particularly when you're editing a plate reconstruction, moving things around, you need to understand how this rotation file works. So that's one of the key inputs. Another one is these GPML files. This is the GPlates markup language. And this is the geometry stuff. So it's a kind of an XML feature sort of thing. And GPlates allows you in most cases to convert GPML to shapefile and shapefile to GPML. Who here uses shapefiles? Yeah. So shapefiles from ArcGIS, QGIS. So there's a lot of interoperability, which we'll talk about as well. But to get started very quickly, all you have to do is find a project file. So this GPROJ file. Okay, so there's 3 of them in here. Maybe start with just the one that's Zahirovic et al. 2022 GPlates.GPROJ, and you can click and drag and drop it onto the globe. That might not work for everybody, but I'll show you the alternative. And the alternative is to go to File, Open Project. Yep, and then navigate to your folder and then select one of the project files. Yes, yes, yep. And click Open, and it'll take a few seconds, but it should open with something like this. How's everyone going online as well? Have we got GPlates? Perfect. Look at this. Amazing. Some gray screens. Yes, good, very good. Okay, so I'll just show that again. It's File, Open Project, navigate to your folder. And again, make sure that it's an unzipped, uncompressed folder, because GPlates can't see inside zipped folders. And then select one of these project files and click Open. Okay, so for those who've managed to do this, you can now start using your mouse to click and drag and reorient the globe. And you can use your mouse wheel, the scroll, to zoom in and zoom out. Okay. If you don't have a mouse with you, that's okay. You can zoom on the on the right-hand side of the screen, and you can even use this numerical value here. Okay, has everybody managed to do some of that? Excellent. Okay, while you're waiting, some of you who are ahead, start playing back the reconstruction. Oh, oh, you can't see. Yeah. Okay.
Yes.
Oh, I can click OK here. Just here. Yeah. Great. Thank you. So you can go back and forth. You can press play, and it will play towards the present. You can enter the age. So this model goes back to 400 million years to the present. So you can press play, and you can still click and drag the globe and start exploring. Okay, so I'll just check that everyone is okay. It's working for most people, I hope. Excellent. Yes, of course. Mhm. Okay, let me just have a look. QT. Okay. I'll take a screenshot of this. Just trying to think. You downloaded the installer recently from the GPlates website? Okay. And you have the same problem. Okay. Can we just check if your computer is 64-bit or 32-bit? Can you? I'll get my phone so I can take a picture of the error message. Yeah. Oh, it would crash. Okay, let's see. Let's see. Okay. Let's just wait. Yeah, we'll wait. I'll come back. I'll just get my phone.
Yeah.
Okay. Interesting. Yeah, that's okay. What's the best way to test this? Yeah. Yeah, so it looks like it's working on the machine. I wonder if the folder is like not readable, like not writable. So let me just see. So, so let's have a look. So you said downloads, and then this one. Okay, so it's a folder. That's good. It's not a zip file. Let's right click, read only. Okay, I think we're going to fix that. I'm not sure why that happened, but yeah, try that now. Okay. 64. Okay. Okay, so then GPlates. Okay. Which but you have GPlates running here. You don't need to install it again. You already have it. Yes. Yeah. Yep. So you're good. You have it working already, and you have it too. So you want to just open the project file, open project. While we're here, I wanted to also describe what kind of files GPlates works with, just to give you a sense of what to expect later. So one of the files is this .rot file. Okay, it's a rotation file, and I can open it in a simple text editor. Let me text. Yeah. Oops, that's not the file, but that's okay. So here is what the rotation file looks like. And later on today, we'll talk about what these columns mean, what these numbers mean. Particularly when you're editing a plate reconstruction, moving things around, you need to understand how this rotation file works. So that's one of the key inputs. Another one is these GPML files. This is the GPlates markup language. And this is the geometry stuff. So it's a kind of an XML feature sort of thing. And GPlates allows you in most cases to convert GPML to shapefile and shapefile to GPML. Who here uses shapefiles? Yeah. So shapefiles from ArcGIS, QGIS. So there's a lot of interoperability, which we'll talk about as well. But to get started very quickly, all you have to do is find a project file. So this GPROJ file. Okay, so there's 3 of them in here. Maybe start with just the one that's Zahirovic et al. 2022 GPlates.GPROJ, and you can click and drag and drop it onto the globe. That might not work for everybody, but I'll show you the alternative. And the alternative is to go to File, Open Project. Yep, and then navigate to your folder, and then select one of the project files. Yes, yes, yep. And click Open, and it'll take a few seconds, but it should open with something like this. How's everyone going online as well? Have we got GPlates? Perfect. Look at this. Amazing. Some gray screens. Yes, good, very good. Okay, so I'll just show that again. It's File, Open Project, navigate to your folder. And again, make sure that it's an unzipped, uncompressed folder, because GPlates can't see inside zipped folders. And then select one of these project files and click Open. Okay, so for those who've managed to do this, you can now start using your mouse to click and drag and reorient the globe. And you can use your mouse wheel, the scroll, to zoom in and zoom out. Okay. If you don't have a mouse with you, that's okay. You can zoom on the left, on the right-hand side of the screen, and you can even use this numerical value here. Okay, has everybody managed to do some of that? Excellent. Okay, while you're waiting, some of you who are ahead, start playing back the reconstruction. Oh, you can't see. Yeah. Okay.
Yeah.
Oh, I can click OK here. Just here. Yeah. Great. Thank you. So you can go back and forth. You can press play and it will play towards the present. You can enter the age. So this model goes back to 400 million years to the present. So you can press play and you can still click and drag the globe and start exploring. Okay, so I'll just check that everyone is okay. It's working for most people, I hope. Excellent. Yes, of course. Okay, can we just have a look? QT. Okay. I'll take a screenshot of this. Just trying to think. You downloaded the installer recently from the GPlates website? Okay. And you have the same problem. Okay. Can we just check if your computer is 64-bit or 32-bit? Can you? I'll get my phone so I can take a picture of the error message. Yeah. Oh, it would crash. Okay, let's see. Let's see. Okay. Let's just wait. Yeah, we'll wait. I'll come back. I'll just get my phone.
Yeah.
Okay. Interesting. Yeah, that's okay. What's the best way to test this? Yeah. Yeah, so it looks like it's working on the machine. I wonder if the folder is like not readable, like not writable. So let me just see. So let's have a look. So you said downloads, and then this one. Okay, so it's a folder. That's good. It's not a zip file. Let's right click, read only. Okay, I think we're going to fix that. I'm not sure why that happened, but yeah, try that now. Okay. $64. Okay. Okay, great. Sorry, we're back. It looks like we had a dropout of the internet. Online, hopefully you folks are doing okay. please put in the chat if you've got any issues, but you should have been able to open GPlates. Okay, you get this screen, which is not very, there's nothing here. You can go to File, Open Project, go to the folder, and then select one of the GPlates project files, click Open, and you'll have to wait for about 20 seconds sometimes. You can click and drag to reorient the globe, reconstruct manually by clicking the back and forth buttons, or go to a particular time by entering a number and pressing Enter. Okay. Now, there is a way to actually use the time slider here as well. But just keep in mind that the plate topologies will only work at the integer time. Okay. And I'll show you we'll talk about the plate topologies later. I'll just walk around and see if anyone has any problems. Yours is still crashing? Let's have a look. Can I have a... Oh, okay. No, we don't want that. Because program files is not writable for the user. So you want to put it in documents or desktop. Okay, I'll come back. Okay, great. So you have, yeah. So File, Open Project. No, that's not going to work because it needs to stay in the same folder. Yeah, so you have to have the whole folder in one location. You can move the whole folder anywhere else, but it just needs to be retained. I open it from there. No, but the folder isn't there. I'll show you. No. So this is a zip file, not a folder. So you need to right click on it and then extract. Okay, so once it's extracted, try doing that step again. Okay, so the key thing, folks, to remember at this stage is I've given you a folder of files and it's easy to load the project file, okay? But you want to keep that folder structure the same, okay? The GPlates project file looks for the relative paths of files. So if you move it anywhere else, it will probably break. It has a backup, which is it looks at the absolute paths as a backup, but it actually then starts looking for the absolute paths on my computer, which you don't have, right? So if you're transferring the project files, you need to keep it with that folder. Okay. How are you guys going? Oh, excellent. Beautiful. Excellent. Yes, you need to extract the zip file. Yep. Beautiful. Click open. Excellent. Okay. That's going to take a minute. Wow. Oh, yeah. So the GPROJ file doesn't actually contain a lot of data. It just points to the files. So it's kind of like just a quick bundle. Like in ArcGIS, it's like the MXD file, just the map file. Okay. Okay, so yes, another reminder, as I mentioned before, these GPlates project files, okay, they're referencing some files in the subdirectories here, subfolders. So if you have a GPlates project file, you want to essentially keep this folder and move that folder, okay, and all of its contents. Because the GPlates project file, if you look at it, it's a tiny little file of 16 kilobytes, and it's just the instructions on what to load and really how to color it, okay? But that's the quick way of getting started, and we'll talk about how to bring in individual shape files and rasters a little later on. Okay. All right, great. Yes, you have a question.
What's the location of the data that you?
Yep. So all of the data lives either inside this folder or rasters and static geometries in the subfolders.
In the raster and stuff.
Yep. And the way that you can find out where those files are is if you go to File, Manage Feature Collections, and then you can hover over a file in the list, and it should reveal to you the full path. So for example, if I want to scroll down to the bottom, and the fracture zones, if I hover over them, they live in a subfolder called Static Geometries and Seafloor Fabric. Okay, so that's a good way to kind of know where the actual raw data is. Okay, all right, so let's now talk about some other things about layers in GPlates. Who here has used QGIS or ArcGIS? Okay, a few people. So it's a similar concept of layering. Okay, so if we go to Window at the top and then Show Layers, the window, you should get a window like this. So that's Window and Show Layers. Okay, great. So this is what controls the visibility and the ordering of layers. Okay, so for example, I can click on the topography, move it to the top, and you can see it will then hide a lot of things behind it. Okay, so that's why often the raster layers, which are these red layers, are at the bottom. Fracture zones, for example, here, I can click the eye icon to turn on and off. Okay, it's still loaded, but it's just hidden or shown. Okay, I can also use this hide everything and then just enable one layer at a time, or I can show everything using this open eye icon. And you can see there's lots of these yellow points that I don't want. They live in this green layer called 33 mesh. That's the velocity sampling mesh. Okay, so start playing around with that. I'll just check that everyone has managed to find the Windows layer, the layer dialog. Yeah, beautiful. Great, you got it to work. Excellent.
Wow. One by one. By one canvas.
Really?
Yeah.
Oh,
That's right.
that's really tricky. Okay. Okay, okay. Okay, you've got the layers dialog. Excellent. It's very good. How are you guys going? Yeah, okay, that's okay.
Okay.
That's why I'm here to hopefully fix some of the problems.
I believe it's in this folder, right?
Mm,
Gimana Mas ditaruhnya Mas? Yang mana? Yang tadi. Ini yang extract. Yeah. Document. This one, right?
no, it's not in this one. It's in the zip file that I
Oh, okay.
downloaded separately.
Okay, I will find the file.
Okay. Do you know where the downloaded folder is? Downloaded zip? Not yet. Okay, I'll come back when you. Excellent. Okay. I'm really curious what happened with your one because it didn't give an error, did it? It just crashed. Okay. If you find any errors, take a screenshot and send it to me because I can then send it to the developers and see what the problem is. It could be, yeah, it could be something to do with OpenGL and the drivers and I don't know. Yeah. Yeah, any information you can get, but yeah, sorry about that. Okay. Yeah, so the good thing about GPlates is that it's cross-platform. So it works on Apple, Macs, Windows, Ubuntu. But the challenge we have is that every computer is slightly different. So it could be like the memory, it could be, a different version of Ubuntu. And yeah, it's a bit challenging to keep up with all of that. All right, excellent. Hmm? Yes. Yeah. So the colors of these layers just represent the broad category of things. So green means geometries, yellow means rotation layer, light blue means velocities. So you can see if I hide the velocities, they disappear. The purple layer is the plate boundaries, which you can see in black. The brown layers are the deforming meshes. Okay. And the red is the rasters. So they can be color rasters or numerical rasters, which we'll talk about later. Okay. So if I now activate just the present day static polygons, just this one, and if I go to the present day, 0 and enter, yeah, you can see that we have these polygons covering the whole surface of the planet. Okay. We can now interrogate those features or any feature you have, any geometry that you have, by going to Feature Inspector, this Africa icon. And you can click on the edges of any of these features. And it will reveal to you some useful components. So we'll tell you the type usually, a name. It will tell you the plate ID. Okay. Now this is really important. We'll talk more about plate IDs today because GPlates uses these numbers called plate IDs to move tectonic elements around on the surface of the planet. Okay. So plate ID 901 is the Pacific plate. And so GPlates will rotate everything with a plate ID of 901 if it has a plate ID of 901. So if you just need to, you have to click on the line. Yeah. Yeah. And if you have multiple adjacent features, you can actually see on the window underneath, there are two adjacent features, and you can select between the two of them. Okay, so the plate ID is what controls the motion. But another really important piece of information is the valid time from the from age. Here is 10.9 million years. So that's when this piece of ocean floor was formed. And so GPlates will make it appear from 10.9. So if I go to 11, it's missing. And by 10, it's present. Okay. So that will relate to any of your own data that you bring in. It will need to be assigned with a plate ID, and it should have a from and a to age. It doesn't have to. I'll show you later why it doesn't have to. But those are the two basic principles of what GPlates is doing. Okay. Has anyone got any issues? You can't seem to click. Yep, that's a common issue sometimes. So if you, oh yeah, you've activate the selection tool and then click on the edge. Beautiful. Excellent. Well done. Yes, so the plate ID and then the age. So here the age, it starts from 0 because this is a mid-ocean ridge, very young crust. But if you click something else, you'll have a plate ID of 701, which is Africa, and a valid time of 20.1 million years to the present. Great. Yeah, so you've done the right thing. So you've selected, and if you click on any feature, yep, you'll get some of these key pieces of information. Yep, so I think you just need to make sure it's activated, and then click on a feature, and it will have a plate ID and an age as well. Yeah, good. Excellent. You can't click the plates? Okay, let's have a look. Thank you.
Hello. Morning.
Okay, so you just need to click this selector and then click on the edge, and it will select any feature. That's really going to be quite important if you start wanting to move things around and change the rotations. Great. Excellent. Okay, was there someone online who had a question?
Yeah. Pak Sabin, can you hear my voice?
Yeah, I can hear you.
Yeah. If we click one of the plate boundary here, so we cannot rotate the globe.
Do you want to share your screen?
Oh yeah.
No. Oh, okay. Yes, that's a good question. Yeah. So if you're clicking around, it's hard to move the globe. So here's a trick. On my Mac, I press and hold the command button on my keyboard, click and drag. And I think on the Windows, it's control, click and drag. Is it? Is it control? Yeah. So control, click and drag. Yeah. So there's a few keyboard shortcuts that will help if you have to do this all the time. But the other ways you just go back to the orientation tool. Great. Good question. Okay.
Thanks, Mark.
No worries. Thanks for following along. All right, the last thing I wanted to show on the visualization things is under here, there's a view drop-down menu. The default view is always 3D orthographic, but you can change it to something like Mollwide or Robinson. And you can get a different projection essentially within GPlates. This can be quite useful if you're looking at a global perspective rather than just a region or a hemisphere. And there's another really useful trick that you can use to change the center longitude. So if you go to View, Camera Location, Set Projection. So View, Set Projection. I can change the central meridian. If we want to look at the Pacific plate, I could change it to 180. I think Indonesia may be 120 degrees east. And you can then see that Indonesia is in the middle of the view. Okay. View, set projection. Yeah, press OK, and you can see the Mercator one is not very useful, to be completely honest, but Mollwide and Robinson can be good global representations. Okay, great. What I want to show you now is how we can export these sorts of things, right, for your own presentations, for your own work, okay? One of the first things you can do is save this project as something else so that you don't overwrite your original project. And the way to do that is to go to File, Save Project As. And I can just name it anything I want and click Save. Okay, so what that means is that if I want to start from that spot, next time I can just load that project. It will remember the files I've loaded, the way they look, and things like that. Okay.
It's the directory path method, or
Sorry?
you can take the file everywhere you want.
Yeah, so that's a good question. It comes back to the previous discussion. The GPlates project file, you can actually save anywhere you want on your computer. However, the moment you move that folder of data anywhere or you rename it, the project file will not work anymore. So the best practice is still to just have it within the folder so that you can have this self-contained workspace that you can move around. Okay? So that's so I'll just demonstrate that. I've just created a project called -ITB. Again, I can drag and drop or go to File, Open Project, navigate to it, and it will remember all the things that I had loaded and what was activated. Okay. All right, let's do something a bit more fun. Let's export this view, say, of Indonesia from 25 million years to the present in, say, 5 million year intervals. Okay. And we'll start as JPEG and PNG files, and we'll export SVG, so scalable vector graphics. And then we'll also separately, we'll export things like shape files and things like that. Okay. One thing that will help you is when GPlates writes out the images, it will just give you the view that you have, okay? But that can be quite confusing. You don't know what age it represents. Okay, the age is written to the file name that's written. One thing we can do is add some text, anywhere on the screen. So we can go to View and then Configure Text Overlay. So View and then Configure Text Overlay. So we can enable this. We can put really anything we want. Instruction, ITB. Leave the %F, that will give us the age. And then, MA means mega annum, millions of years. But if you're showing this to school children, maybe you can put it as millions of years. Or if you're creating this for the public, you can change this. You can change the position, the anchor in the top left, top right, bottom right, left, bottom right. Choose the text color, choose the text font. Sometimes it has to be quite large text, you'll see. I'm just going to do bottom right. Okay, so you can see it's probably too big for me. So I go View, Configure Text Overlay. I'll make the font smaller. Okay. Have most people managed to get that done? I'll just walk around. I'll get lots of steps today, I think. That's good. Beautiful. Amazing. Yes, excellent. We have some text. Beautiful. Yep, so you go to View. Configure Text Overlay. Yep, and click Enable. You can change the text here in the font and then OK. Beautiful. Yeah, so tick that one. Beautiful. And then you can change the text. Oh, you've changed the color. Very good. Excellent. How did you go? You got some text? Oh, you do. Excellent. Yes, some text. Very nice. Very nice. How did you guys go? Beautiful. Yeah. Yeah. Beautiful. Oh, you've got it. Oh, good. Perfect. So to get the text, you can go to View. Yeah. And then Configure Text Overlay. Yeah. And then tick this, enable the text. So this one, tick this one. Yeah. And you can change the text or you can just click OK and you'll get something. All right. Great. Okay. Let's now do some exports. We can go to Reconstruction and Export. So this is a very important menu location because it contains all the export options. So GPlates will export for you the reconstructed, the paleocoordinate version, whether it's the images or shapefiles or whatever else. This is where it lives. So reconstruction, export. And you get this window here. You can export a single snapshot, but most of the times I just use this time sequence. Okay, so we said from 25 to 0 with an increment of 5 million years. Okay, and then here you can add the export types, and there's lots to choose from. Okay, so I'll just do that again. So reconstruction, export, change the export from and to with some increment values. And then if I click this button here, add export type, you get lots of options. Okay. So over the next 2 days, we'll go through more of these. I'm not going to show you all of them right now because there's too many. So the first one is we want some images. Maybe you want it in a presentation or a paper or something. You can choose JPEG, and you can specify the output file name if you want. You can set the export resolution. Just make sure you click on this constraint aspect ratio if you change this number. And click OK. And so the first export type is an image, which will be a screenshot as a JPEG. We can do the same thing again. Click on Add Export, Image Screenshot, and do the same thing with a PNG. The PNG can be quite useful because it's the portable network graphics, and it's got the transparent background. And you can click OK. We can also export the scalable vector graphics if you have Adobe Illustrator or some other vector graphic editing software. So we can go to Add Export, Projected Geometries, SVG, and OK. The reason why the SVG option is really useful is that GPlates has very limited symbology, like, controlling the thickness and colors of lines, any other kind of symbology. It's easier to do in scalable vector graphics output. The other really important option here is the target or the output directory. Make sure you put that somewhere where you have write privileges. So My Documents is okay, but just make a new folder, because this will generate a lot of new files, okay? This could clog up your whole directory. So I can create a folder called ITB, open, and I can click on Begin Export. Okay, so this is the output that I'm getting. That's right. Yeah. These are the PNGs. You can see they have the transparent background. And these are the SVG scalable vector graphic files. So let's just test this. Okay, so you can easily bring these things into PowerPoint, annotate them further. And you can see the difference. This is a JPEG with a black background, and this is the PNG. Send to front. Okay. If you were like, okay, I want to do this every 1 million years, well, you just change the increment and click the Begin Export, and GPlates will do it actually quite quickly. And I'll export the whole bundle of frames. The text will follow the age, but you can see that only this part with the percentage F will change. Okay. And so that's very useful because, yeah, look, you have the age in the file name, but it's quite useful once you bring it into PowerPoint or a document, you can still see the text. You can see also the choice of color of the text can be quite useful. On a PNG, well, white white on white is going to be hard to read. So you can just play around with that. Okay. I'll walk around and check how everyone is going. Yes.
Yeah, 0.2.
Yep. Yep. This is a great question. This is a great question. Keep coming with those great questions. Okay. The question was, in the export, what does this percentage 0.2 F mean? Okay. So this is essentially a code to tell GPlates how to format that age. Okay. What this really means is have 2 decimal places in the age. And that's it, right? You can see down here, there's other options to choose from as well. So there's the reconstruction age in, as an integer. So that's %D.
So it won't show the decimal.
That's right. Exactly.
If I type it, then there will be 3 decimal.
It will be 3 decimal places. That's right. Exactly. The reason why this option is really, really useful is GPlates, unfortunately, still doesn't have the ability to export animations. Okay. So what we all have to do is export them as frames, and then we use FFmpeg to stitch together the frames to make an animation. Okay. However, FFmpeg is very pedantic and very picky because it wants frame numbers. It doesn't care about the geological age. So, for example, I'll have to use something like frame number from 0 onwards, %U. And you can see that it's creating those frame numbers. Frame 1, 2, 3, 4, 5, 6. And importantly, it's padding it with zeros, which makes FFmpeg happy. Okay. So but the same can be applied to your text overlay. So I think maybe I don't remember actually testing this. No, that didn't work. Oh, damn it. It should work, but it doesn't. We can change the decimal places here instead. Okay. Okay, so that's some basic exports of the images or the screenshots, and also the scalable vector graphics. So hopefully, if I can go to Adobe Illustrator or whatever. Okay, so this is just an example of a view in Adobe Illustrator. I can isolate, all the plate boundaries, change the thicknesses of the lines, change the colors very easily, add more symbols, stars, arrows, whatever. Okay. So I know that we also work with Inkscape, which is an open source scalable vector graphic editing software similar to Illustrator. Okay. But that's the SVG export. Is that making sense? Does anyone have some issues? I'll come around again. Okay. Yep. So to check the age, make sure that your age, I mean, here you can say Sabin is bad at tectonics. Okay. And it won't change, right, at all. Yep. So instead, if you add the percentage F, I think. %F. Yeah. So percent FMA. Yes.
I explained that 0.2 represent the decimal, so we can set the increment lower than 1.
So yes, so technically you can set the increment to lower than 1, and GPlates will definitely happily export it, but the plate boundaries might get broken because they're only valid at roughly 1 million year integer values. So if you actually want to do it at sub 1 million year intervals, you can just hide your purple layer of the plate boundaries. Okay, so you can just hide that, and GPlates, what it will do is interpolate the position of all the tectonic elements at the finer temporal scale. Yeah, very good question as well. Great. Okay. Wow, you've gotten straight into the science. Look at that. He's reconstructing Sunderland. Yeah, you've got the age text. Good. Excellent. Yes.
To the free.
Oh, yeah. Yeah. So you just need to go to view, configure text overlay, and then change the decimal here. Okay, great. Okay, any questions here? Yes.
We start to export
Yes.
file, right? We
Mhm.
start to add 50 MA.
Yep.
And then we want to see before this. How is it?
Oh, okay. Yep. So it can get changed to reconstruction and then configure animation,
Oh,
and it changes this. So good question. Good tip. This I will remind people. Oh, sorry, folks. Okay, so we've had a question here that when you specify the export ages, GPlates will automatically kind of reset this time in its animation here in the window. You can go back and reset that by going to reconstruction and then configure animation. Okay, so you can animate from 410 to 0. That's the full range. You can reverse the time, and yeah, you can do lots of things. So if I click close, I can go back now and it will play the full time. But yeah, so you had a question about the sub 1 million year interval. So see what happens here. This plate gets broken at the sub integer ages, and it's to do with how the plate boundaries interlock. If it's missing one or more plate boundary features, it will not know how to close that topology. And I'll come back to this today. We'll talk about that, at much more length. Okay. Excellent. All right, so the next export functionality I want to show you, or two examples, which I think will be quite useful to you, is exporting shapefiles and exporting geotiffs. Okay. Yep. Because, many of us still work with QGIS, ArcGIS, and shapefiles and geotiffs can be quite useful. So we can go back to the reconstruction and export window. We can remove what's already in the list here, and then add export type. Now we can add a color raster, which is a geotiff. Oops. So add export, color raster, GeoTIFF, and OK. So that will give you a GeoTIFF as a color. GPlates, we'll talk later today, can deal with numerical rasters as well. So if you have like elevation as numbers, it will reconstruct them as numbers. And so that's what we call a numerical raster. You can export that as a numerical GeoTIFF, or you can even export it as a numerical NetCDF grid, which is what many people work with as well. Yep. So color raster was the first one. Color raster, GeoTIFF in the bottom left. You can muck around with this on the right, which is the resolution. Again, you can muck around with a name, template, the region, if you're really interested, and you can click OK. And then again, change your export time and your increment. If I click on begin export, it will do the same. Okay, so I'll just demonstrate to you what's happened. I've now been provided from GPlates the reconstructed present-day topography back through time. And so this is a good place to remind everyone, like, GPlates is often working with present-day geometries of, say, coastlines and topography. And part of it is because it's just easy for the eye to follow. Okay. But of course, the elevation is meaningless in a way the further you go back in time. You 60 million years ago, you don't have the Andes, you don't have the Himalayas and so on. But it's just for us sometimes visually just to see which part of the world, plate is moving. We can track that through time. So hopefully, if I get QGIS to open, I don't know why it takes so long. I guess this is why I drink so much coffee. You just like press a button and you wait. So you need some tea or coffee. So if I click and drag, you can see in QGIS, it's exported the reconstructed position of these things and the raster. Okay. I'll show you as well now how we deal with shapefiles. It's, again, very simple, very easy. If I go to add export type, reconstructed geometries, I can choose shapefiles. Does anyone here work with generic mapping tools? Yeah. GMT. So here you've got some nice options for GMT export. Okay, so we've got, if I choose shapefiles, I can click on OK. And again, just click on begin export. And GPlates is truly amazing in how quickly it reconstructs and exports, reconstructed rasters and reconstructed geometries. Okay, it's very, very efficient. And what I've done here before is exported the 15 million year time snapshot. And I can then in QGIS or ArcGIS add the 15 million year shapefile. I can change the symbology. I mean, maybe by plate ID. Display. Yeah. anyway, so you can see what I've done here. I've exported things, and it will remember like all the tectonic element names, so it will preserve the metadata. You can use QGIS to label things, and yeah, so it can. That's a really important interoperability with GIS software. Do you have a question? Not yet?
Sorry. Hello,
Yes.
Mr.
Hello.
Sabin. Hello. Could you reply from how we export to the shape file, please?
Yep. Okay. Good questions. Thank you, everyone. All right. So I'm just going to show that again. So if we go to reconstruction and export, okay, this is that main export dialog window that you get. And remember, we just had to put in the from age, to age, the increments. This is where you specify the directory, the output. I think that was the question. So you can click on these three dots, specify an output directory. You can create a new folder, for example, and then add the export data type. So we can click on this button here, add export. For the shapefiles, it was under reconstructed geometries on the left menu. And then at bottom left, you can choose shapefile and click OK. Once you're happy with these options, you can click on begin export. Now, the cool thing is that GPlates will export these things per layer. So if I go back again and re-export, see how it's preserved it in subfolders. So now you have the coastline features, terrain boundary features separately, and so on. Okay, so you can then relayer, you recreate that cake in QGIS or ArcGIS. The plate boundaries are a bit trickier. You need to actually export them from this option here, the resolved topologies. Okay, but again, you just choose shapefile, click OK, and begin export. And it will export the full plate. It will export the subduction zones separately from the mid-ocean ridges. And that way you can deal with your symbology. So for example, if I try to find subduction boundaries at 15, so where's the SHP? I can't see. Feel like I'm going blind. Oh yeah, it's because it's sorted that way. SHP. What is going on? Here it is. Okay, so did you see that the subduction zones they were added as well at 15 millimeters? Okay.
Okay, thanks.
So essentially that was a quick way to get everybody started. You should now be able to open GPlates, drag a project file, and export things pretty quickly, right? When you get quick at this, it'll take you 2 minutes really to export some existing reconstructions and make animations, as we mentioned, using FFmpeg. And then we'll talk about, I guess, the more advanced features in a moment. Yeah, great question. Okay, for the image, the screenshot, it will just export what's zoomed in your frame. But if you export the numerical raster or the color raster or the shapefile, it will export the full global extent. And then you can control that frame in QGIS or ArcGIS. Okay, so that's, yeah, very good question as well. Yes, yes. So it's the present day coastline. Again, just really for us to visually see where our favorite part of the world has been in the past. When we start talking about paleogeography, we'll talk about paleo shorelines or paleo coastlines, and that's trickier. That's where people disagree a lot more, and so it's best for people to bring in their own models. But yeah, no, this is just the reconstructed present day coastline. Yes.
It just export anything that we show in the layer.
Yes, exactly.
We have, I think, layer. We have many geometry.
Yep, exactly.
We export it just what we show.
Exactly. So it will only export what's activated and visible. And there is a button to merge all of them into one, but I'd never recommend doing that with shapefiles because it gets messy and just keep in mind sometimes the export can contain multiple types of geometries. So it could be point data, lines, and polygons. But GPlates is smart enough to know that shapefiles can only contain one type of data. So we'll actually split them into three. Yeah. So you can very quickly end up with lots and lots of files. Yeah. Yeah. PNG and JPEG is just the zoomed areas. Yes.
I'm Robinson's. And
Yep.
then the meridian's position is in Indonesia. But when I export it into the zip file, the result is like this one.
Yeah.
Not like a image.
Yeah, exactly. So, but that's on purpose because the screenshots, the images, the PNG and JPEG will export whatever you see in GPlates. Okay. But the shapefiles will be exported in the WGS84 global coordinates. And so you can control your projection and the frame in QGIS. Yeah.
Into GIS. So I'm not.
Just set the CRS
This
in
one.
the GPlate. And
In QGIS. Yeah.
System.
but right.
Did you guys manage to open up GPlates? Oh, you did. Oh, no, you're just following along. Okay. Do you want to open it yourself or you just want to follow along? Yeah, fair enough. Yeah. Yeah, it's recorded. So, yeah. Great. Okay. Beautiful work. Wow. You guys are very impressive. You've never used GPlates before and you're experts already. Yes.
Area where we want to show because by default it shows the global. Can we construct the area to be smaller?
Yes. You can set the region extent here, the top latitude, bottom latitude, and the longitudes. And I'll show you the next trick that will help with this as well, which is quite important. So we'll come back to this. Any other questions, any troubles here in the audience? No, everyone is following along. Well done. Very impressed. Okay. Okay, so just a reminder again, now that when I go through GPlates and I go back and forth, it's taken over the time stepping based on what I put in the export dialog. And I can go back to reconstruction, configure animation, and essentially reset that back to 410 to 0 in 1 millisecond intervals, close. Okay, so we get all of that exported. Okay. GPlates is, I'll talk about, I guess, other plate reconstruction software that existed in the past. But GPlates is very fast in how it handles data. Part of the reason is that the lead developer of GPlates, John Cannon, he is an amazing talent. But he came from the video gaming industry. Okay. So everything is accelerated on the GPU and everything's really fast. Okay. So I'm going to demonstrate to you how easily GPlates like recasts things into a different reference frame. And so we'll talk about that a bit later, reference frames, right? Sometimes we're just looking at, I don't know, Sumatra, right? We want to know only what is happening with respect to Sumatra. Okay, we want to say keep Sumatra fixed. Okay, and I mentioned to you at the beginning of today that GPlates identifies each tectonic element with a plate ID. Okay, now when I say tectonic element, I just mean usually a terrain, right? And of course, you can introduce more terrains. We used to have a limitation from the old plates program from the 1990s that it could only have 3 plate ID, 3 digits, but now it can have 10 digits. And so we have lots and lots of terrains and polygons and so on. Now, by the end of tomorrow, I hope you will memorize every single plate ID, right? But if you forget, it's okay because you can activate the select tool. And if you click on Sumatra, for example, the plate ID is 673. Okay. So there is no search feature, unfortunately, but you can do it in QGIS or ArcGIS. You can do a find. Yeah. So the ID will be exported here. So for example, if I look at the attribute table, I'm confused. Oh, that's the anchor and the plate ID. Why is the plate ID 0? Yes, I mean it should give you some numbers like this, right? So you can search for plate IDs in here. Hang on a sec. I'm getting myself confused. I don't understand why the plate ID is 0 actually in here. But anyway, we'll come back to that. So there's no search feature in GPlates, but yeah, you can identify the plate ID just by clicking on it and finding the plate ID. And so if I go to reconstruction, I can specify an anchored plate ID. So I can go 673 and click OK. So what you noticed is that GPlates automatically on the fly using the GPU is essentially rotating everything to be moving with respect to this part of Sumatra. Okay, so that might help you, for example, see, okay, what oroclinal bending model, I put in for Sunderland, and it can highlight to you the relative plate motions, okay, the relative kinematics between the terrains. Because when you have it in the default view, where the anchored plate ID is 0, okay, that's the reference frame, which we'll talk about later. That includes both relative and absolute plate motions, which I'll talk about later, right? So it includes the relative motions, but then it also includes the entire plate circuit of the Earth that's there. So again, I can change this to any other feature. 801 is Australia, and that will keep Australia in its present day coordinates and then move everything with respect to Australia. So that can be quite useful if you're trying to create an animation So things aren't moving around too much, particularly over like 400 million years. Things move a lot. So that's one way to do it. And again, GPlates, when you export these things, will embed that anchored plate. Okay. So what you see in GPlates is what you'll get in QGIS or the scalable vector graphics in Inkscape or whatever. Okay. It will also recompute all the velocities. So if I now look at Kalimantan 614, I'm guessing you've memorized all the plate IDs already. So there's Kalimantan. And you can see from this model that all the velocities that, for the whole world with respect to Kalimantan. Okay, so it's recomputed. And so for some of you who might be interested, for example, let's just have a look at, so 301 could be Eurasia. Okay, that's this area here, that's anchored. You can see the plate velocities with respect to Eurasia. You can export these as well. So let's do that since we're talking about exports. So if we go to reconstruction, export 50 to 0 in 10 million intervals. Here under velocities, there's a few options, and I only really recommend one, which is GMT, the ASCII text file. The Sitcom S global is for the geodynamic mantle convection model runs. So when I run a geodynamic model, I export the velocities and it helps run the convection. And this is another convection code called Terra. So this is what you want, GMT XY. You can export to a single file. This can be quite useful for some of these meshes that are made up of multiple components. And this is very important here, the velocity vector format. The Cartesian 3D vector can be quite useful if you just want to look at displacements in centimeters per year in the east-west direction, north-south direction. And the Z should be 0. There's no vertical component. And so I use this when I'm running landscape evolution models because I can actually displace the surface and move things around. But for most of my plotting, say in GMT, I use this last option here, which exports the azimuth of the velocity clockwise from north in degrees. Okay. And it exports the magnitude, which is the speed in centimeters per year. So if I click on OK, begin the export. And this is where, if you've got some Python or GMT skills, it becomes really handy because you get lots of files and lots of data like this. Okay. So at 30 million years ago, this is in the file, it's telling you in the header with GMT code some key things. So for example, what was the anchored plate that you used? Because that can change things dramatically. It'll tell you what you had loaded, but importantly, this is what you want, okay? So this is the longitude and latitude of the sampling point, the mesh node. This is the azimuth, clockwise from north, okay? And this is the speed in centimeters per year, so 0.83 centimeters a year at that time. And the plate ID, it's sampling at that position is 0, which means it's probably not in one of these tectonic plates. But yeah, essentially, if you see numbers here, so 301 is what I had anchored, and the speed is 0, okay, because it's being held fixed. But 701 Africa, so this is the speed of this point, okay, longitude, latitude, That's the azimuth. It's northward, and it's moving at about 1.2 centimeters a year with respect to Eurasia. Okay. So this covers the whole globe, and you can do all sorts of statistics. You know, what are your terrains doing? For a lot of our work, we want to use the geological constraints, but build in plate motions or terrain motions that are sensible, because from the geological record, right, it looks like the Indian plate has moved the fastest as far as we know. It's moved about 22 centimeters per year for a 10 million year period. It's a very special kind of edge case. So if you have a terrain or a big plate that's moving at 100 centimeters per year, you probably want to think about it and be like, I'm 100% sure of this, it needs to be the case, right? So, you know, we want to build plate tectonic reconstructions that are meaningful and realistic, okay? And we'll come back to the kinematics tool after the break. But before we do that, I wanted to just kind of go through some of the theory, because it helps kind of summarize many of these things we started to talk about today. So look, the basic concepts to start with, we're dealing with a plate tectonic reconstruction software. In this case, it's called GPlates. It's a kinematic tool. So the user has to put in, you know, how the tectonic plates move, okay? And that's controlled by the rotation file, which we'll talk about in a moment. But essentially what we're trying to do is represent numerically the motion of these terrains and ocean plates and continental plates through time. These plate reconstructions allow us essentially to undo, say, seafloor spreading to recover the past state, such as Pangea. The problem we have in deeper time and in complex regions like Southeast Asia, like your neighborhood, is that seafloor has been subducted completely, right? You go to do your mapping in the Luke Ulo Maratas suture, which by definition is the ophiolites that have been lost to subduction through Australia and Eurasia convergence, okay? So for the deeper time reconstructions, we have to rely on other pieces of data. So it could be the sedimentary affinities. It could be your fossils. We also use paleomagnetic data that tells us the latitudinal positions. But all of these things have lots of noise and uncertainty, right? So even the reconstructions of Southeast Asia, of Indonesia, you know, even the last 20 to 50 million years, there's still lots of debates. And I think, you know, you folks here are the ones who will fix all of those problems for us. Okay, so the plate reconstruction software, I guess, landscape is that there is a tool still called a GMap that's free and available on Windows. And GMap is great, particularly for paleomagnetic data. So it has some inbuilt tools to process paleomagnetic apparent polar wander paths and stuff like that. So it's quite useful for that, but it's very simple for everything else. It doesn't show plate boundaries. It doesn't reconstruct rasters, and so on. There's a proprietary industry tool called paleogis, and I think it's for a license. It's like, I don't know, hundreds, probably thousands of dollars per year per user. And of course, there's GPlates that I mentioned to you before. And GPlates being by design open source, a community tool that's maintained by you know, our developers, funded by the Australian government. But there is a global community, and it's by design also interfacing with other open source tools like Inkscape or QGIS and things like this. Okay. GMT and so on. So GPlates has been used, of course, in plate tectonics, geodynamics, paleogeography. We'll start talking about it a bit tomorrow. Paleobiology, people are using it, of course, to understand where their fossils were in deep time. It's used a lot in maybe, well, maybe your colleagues in the other building might be interested in oceanography, ocean circulation, atmospheric circulation, paleoclimate, and more recently in things like data mining, right? You want to maybe know what kind of tectonic setting your ore deposits formed, your nickel or your copper or your gold. And so you can extract these sorts of parameters from GPlates. Yeah, so as I mentioned, it's cross-platform. You should be able to use it on most computers. And I will come back at some stage to talk a little bit about the Python API. Anyone here use Python and coding? Not yet? Okay. Some students. Okay. Yep. So look, I'm not going to dwell on all of this, but yeah, this is kind of the interoperability with some of the geodynamics codes. And this is the QGIS, GeoMap app, ArcGIS, GMT, Inkscape, Adobe Creative Suite, and there's a whole bunch of things that interface with Excel as well. So in the last 13 minutes, I think it's kind of good to come back to see, okay, well, how is GPlates actually moving those things on the globe, right? Because that's what we want to do over the next day or two, understand how it's doing that and how you can modify those rotations, okay? So in plate tectonics, it's essentially numerical theory, right? It's quantitatively describing the motion of rigid bodies on the surface of a sphere. And you can describe that motion using what we call Euler rotations. And that Euler rotation is defined by the longitude and latitude of the axis of rotation, okay? And then angle of rotation is the magnitude, the speed of that motion. And in GPlates, it's always represented as motion between two fragments or tectonic elements, okay? And so the motion between plate 1 and plate 2, you can see this would be the axis of rotation or the pole, Euler pole. And then you can see all of these mid-ocean ridge segments, okay? They are great circles through the pole of rotation. And then we have these things called fracture zones and, well, transforms, sorry, and then fracture zones. And they are perpendicular to these great circles, okay? Anyway, those highlight the actual rotation and the motion between two elements. And so we can see that in the real world, right? So if we just look at the North Atlantic here, and the Central Atlantic on the right here, if you look at your transforms in your seafloor spreading, in your oceanic crust, and if you draw a great circle that's perpendicular to the transform, they essentially coincide with in a point, which is the pole of rotation or the axis of rotation, okay? There is some uncertainty and there's noise because of the geometries of these things, but that's what you're seeing. And so in GPlates, this is what the rotation files look like. We'll come back to that probably tomorrow when we actually start modifying the reconstructions. The first column in your rotation file, which is a simple text file, okay? The first column is the plate ID we mentioned before, okay? So plate ID 101 is North America, and plate ID 101 moves relative to Western North Africa, which is a plate ID of 714, okay? The second column is the age in millions of years, and then we have the Euler pole. So this is the latitude, the longitude, and the angle of rotation from the present day to this time. Okay, so now we're getting very technical and you don't need to remember these things, but if you need to come back to this, it's in the recording and it's here. And these are what we call total finite rotations, okay? Total finite rotations. And what it means is that this number can recover the relative position between North America and Africa at 33.1 million years in one total rotation. Okay. The other one is what we call stage rotations, and they're incremental rotations. This is a total rotation from the present day to 33.1 million years ago. This is also why GPlates stores everything as present day geometries. Okay. So it's easy for your data because often your data is present day geometry. So that's fine. GPlates handles that without a problem. If you digitize something in the deep past, it will then apply the rotation and bring it to the present day. That's how it will store that data. The other thing that's really important to mention here is that you can see there's a rotation every 10 or so million years. That's determined by your temporal resolution of your magnetic anomalies in the sea floor. You can have more temporal resolution than this, but just keep in mind those are those numbers. Now, GPlates is amazing in the sense that it can interpolate the positions, the relative positions at any time. You can compute to any, an age of 1.756, whatever, and it will interpolate the finite rotation at that time and make everything be in the right position. Okay, so those are the Euler rotations. How GPlates knows how to move around a terrain or some fossils is that it needs those plate IDs. Okay, and these are the plate ID definitions. And I showed you at the present day those static polygons that cover the whole surface of the planet, each having a plate ID related to a particular plate. So 801 Australia covers, all of these polygons here. So it means when we talk about like rotating rasters or vector data, GPlates cookie cuts those things. It knows what plate ID is needed, and then it rotates and moves it back in time. Okay, so that's how that works. So this is what those static polygons might look like in an ancient version of ArcMap. But the other thing then to remember is that in GPlates, as I mentioned, everything is recorded as a motion between two plates. Okay, one plate with respect to another. To get a global motion model, it's best practice to have what we call a hierarchy. Okay, relative plate motions in a circuit back to some bigger tectonic element. Okay. Now, at the present day, in GPlates, you can actually make any individual terrains move independently, directly straight to the spin axis to 0. Okay, but that's not always best practice. We try to do that only when we're dealing with paleomagnetic data. But what this means is that the motion of Antarctica inherits the motion of Africa and the hotspots. Okay, so you get this whole plate circuit. And tomorrow we'll talk about And we'll go through the steps of actually modifying these rotations and this hierarchy and circuit if we need to. But you have to remember that GPlates will record your new position in the rotation file. If there's existing rotations there, GPlates will try to interpolate between them. So you can actually create artifacts or, really high plate velocities. And I'll show you how to manage that and comment out and delete the old rotations. But I just wanted to flag that today. And after the break, we'll get into the Kinematics tool, which helps you visually see, well, what's the velocity of a particular tectonic element with respect to another one, or its absolute motion, and so on. Okay. But there's lots of plate reconstructions and times in the plate reconstructions where these things are not the case. And this is why I say to people how important it is to, improve any existing reconstructions, because they might actually have problems. They might not conform to the data constraints. They might not even conform to the rules of plate tectonics. The reason that it's so important is if you're running, say, data mining workflows to look at like, okay, well, what's the convergence rate at this subduction zone and the ore deposits that formed? If the convergence rate is negative, can you really trust the results? And the clear answer there is no. Okay. And so like, yeah, I think at the moment we're still in that kinematic frame of mind. We move things around. But I suspect in the next few years, there'll be like AI guidance and tools that will be like, hey, Sabin, what you've put in here is probably wrong. Maybe check it. And this can be really hard to do in a very complicated region like Southeast Asia. One of the other ways that I try to increase confidence in my models and reconstructions is to try to make sure that the reconstruction in a region doesn't break the adjacent regions, right? It should all somehow connect rather than be, have its own geodynamic rules in this little part of the world that I'm looking at. So I hope that gives you some insight. Mhm. Yeah. And I think that's the case with almost all modeling tools. If you're looking at numerical rift models, you need to know about the viscosities and the temperature dependence of viscosities and, internal heat generation, with any model, right? There's lots of dials and knobs to twist. And if you don't know, if you don't think about these things, you can produce something that looks nice, but it could be completely scientifically impossible. And I see this actually semi-regularly with the reconstructions. And these are, like, we're talking about some of the groups, like big groups globally that should know better. Okay, great. So we break now. I guess we reconvene at 1 o'clock. Yeah. Excellent. All right. Thank you, everybody. And look, if you're all busy, like, I don't expect everybody to come back for all 4 sections, right? But at least this morning, you should be comfortable enough opening GPlates, getting it to work, doing some exports. And then, yeah, we'll just dive deeper into the different components. All right. Amazing. Thank you, everybody. Okay. Welcome back. I hope everybody online can still hear me okay. Hope you all had a nice lunch and nice break. Let's just go back to, I'm going to share my screen. So I just want to go back to this slide. So this afternoon, we'll focus on these tools and functionalities. We'll talk a little bit more about kinematics. We'll start talking a little bit more about reference frames, plate topologies, how to build actual evolving plate topologies and what they are. We'll talk about rasters, high resolution, low resolution, global, regional. And then we'll talk about the time-dependent rasters, the things that change through time. It could be your precipitation, or it could be your dynamic topography for mantle convection. And at some stage tomorrow, we'll also talk about the deforming reconstructions. There was a question about that. But yeah, we'll get through, I think, quite a lot. Okay. So I'm just going to recap very, quickly on all the things we were doing earlier today and get us up to speed with this afternoon. So this morning we started talking about, it's important that you unzip, uncompress any zipped folder, because GPlates can't look inside zipped, compressed folders. Okay. We talked about how it's tends to be quite important to preserve the relative paths when you're dealing with GPlates project files that contain the instructions on like which files to load into GPlates, what's activated in the layers, and so on. So we went through the process of opening a project file. I showed you two ways. One is drag and drop, and one is file, open project. We talked about saving projects and, workspaces that are portable, that you can create a model, GPlates files, and you can share it with your colleague or your supervisor or whatever, and it will still work. Okay. It's just good practice, because even myself, sometimes I'm rushing and I just save a project file somewhere in my computer. And as soon as I rename that file, folder, or I move to another computer, it no longer works, and I get angry at myself. But okay, so we then talked, just before the break, we talked about relative plate motions, how we can anchor a particular plate. And so we'll now delve into how we can get the kinematics out, right? So before the break, I showed you how we extract the velocities. And so, for example, computationally, I would just grid up the velocities and I would extract these things from scripts. But I'll show you that there's an easy kinematics tool that can do some of it already in the graphical user interface. That's pretty easy to use. You can export it to Excel and plot it up and see what's going on. So let's start with that. If you've got the model loaded, the GPlates project file, let's change the anchored plate ID to be back to 0. So reconstruction, specify anchored plate ID, type in 0 and enter, or OK. And in this case, in this model, the anchored plate of 0 is the mantle. Okay. We'll talk a little bit more later about reference frames, but that anchored plate ID is really, really important. Okay. And I'll explain later why. But anyway, so now we have the global model. It's showing us the velocities, the plate boundaries, and so on. So say you want to look at Australia's northward motion as it's crashing into Indonesia, okay, as it's uplifting the mountains in Kinematics tool. Okay, so then you get this kind of blank screen and there's not much there. You can manually enter a latitude, longitude, its plate ID, its anchored plate ID, and some other features like the begin and end time. Or you can cheat a little bit and you can select a feature. So remember this morning we used the Africa little selection tool here. Just realizing there's a bit of a lag with the online, so I'll just go a bit slower. So there's the feature inspection tool, and we can just select any of the islands of Australia. It doesn't really matter. And if you go back to your kinematics tool, you can press this button at the top left that says use focused feature. Okay, and so see how it generates a table with lots of numbers, right? So just select any thing and you click on use focused feature. Now the challenge here is that just keep in mind that if you've selected a polygon or a very large coastline feature, I think it just chooses a random point along that boundary. And when we talk about Euler's theorem, the velocity is slowest, the speed is slowest near the pole, and it's highest at the Euler equator. So, where you choose your point on Earth's surface can actually determine some aspect of those kinematics. Okay, so just keep that in mind. But this is just a quick way. If, for example, here's another little trick. If I hover over Sydney, where you're going to come and visit me in summer, you should be able to see. Let me see. I've got a pointer. Will the pointer work? Oh, no, that's not really that useful. Can you see this thing at the bottom here that says mouse, latitude, longitude? If I hover over Sydney, let's put that in, what is it? 33 south and 150 east. And so I can do this now. I can say, okay, 33 minus 33 and 150, press enter. And now it's tracking the kinematics of Sydney. Okay, my backyard, that's specifically. It's detected that it's 801, the plate ID. From what we had before, we used the selected or focused feature. And here it's detected the anchored plate ID that we've told it. It's looking in the last 200 million years. You can change this. The model goes back to 410, so you can, extend it all the way back. You can change the steps to be 1 million year intervals. But let's just focus on the last 100 million years of what Sydney was doing in 1 million year intervals. It's also really important at this stage, if you use the kinematics tool, to change one of the settings. So in the bottom left, if you click on settings, for whatever reason, and I disagree with this, and I will talk to John again about it, but the velocity time step I want usually is 1 million year time stepping. And the reason is that this is the exact same time stepping the velocity arrows on GPlates have. Okay, so it's comparable. You can hear also, there was a question before about how can you tell if your model is potentially not doing great? You can change these velocity warnings. So say if it's over 15 centimeters a year, it'll be yellow. And if it's moving at over 20 centimeters a year, it'll be red. We can apply, close. We can click on update and it will recompute these things. Okay. Now, at the bottom here, it's not that exciting, but we can, on the right-hand side, we can click the top button here, which is auto scale the y-axis. So it tells us that Sydney used to be at 58 degrees south 100 million years ago, and it's gone north. If you're thinking about paleoclimate, you can think about just the basics of, well, your continent or your area is moving closer towards the equator, okay? So that's the latitude. You can look at longitude. I think longitude is not that useful, to be completely honest. But we can look at speed or velocity magnitude. Okay, this is in centimeters per year. Okay, so from this chart, what can you see that Sydney is doing the last 100 million years? Are there some major changes that you notice? Yeah, when does it go faster? Yeah, so during this last 40 or so million years ago, it's going from a speed of about 1 centimeter per year to speeds of 8 centimeters per year. Then it seems to slow down and maybe speed up again a little bit. Okay, so you can then already start to think about, well, what are the plate driving forces? Why is it doing that? Why is it changing speeds, right? And in the case of Australia, one of the key things, of course, the dominating plate driving force is slab pull. So for example, at 43 million years ago, we abandoned seafloor spreading on the Wharton Ridge. So if I go back to 43, 44, see how the Indo-Australian plate used to be separate? There was a plate boundary here called the Wharton Ridge, and it intersected somewhere in Sumatra. And, you know, this light area is subducted seafloor. So we don't know exactly where that ridge was intersecting Sumatra. But you can already see that maybe you, with your field work, if you look at the kind of rocks you might expect to see, maybe you might want to look for adacites and other rocks that indicate a slab window, and that will tell you more precisely where that mid-ocean ridge is intersecting this margin, right? So that's just an example. But after 43 million years ago, the Australian plate is moving with India. India is colliding up here already with Eurasia, so it's slowing down. But Australia is still going northward. This is my model. It's probably wrong, like most models. They're probably wrong. But you can see there is some slab pull perhaps that could explain these sorts of speed up in the velocities, okay? We can also then look at what is Australia doing relative to Antarctica. So if you want to isolate this seafloor spreading system, you can try to remember all the plate IDs, or you can click on Antarctica, which is a plate ID of 802. So if I change this anchor plate ID box to be 802 and click update, you then see a much cleaner signal of just the Australia-Antarctic seafloor spreading history. Okay. You can also look at the velocity azimuths, the directions of the plate. And then there's some other things like angular velocity, which, I mean, is not that useful to me. I just use the velocity magnitude. You can export this as a Excel spreadsheet. So if I go export table, I can just say Australia, Antarctica. It's a CSV. Bless you. And you can see now you have all the data in a table that you can then plot up. Okay. I'll just walk around and check that everyone's managed to get something to work with the Kinematics tool. Okay, great. I see some Kinematics features. Beautiful. Okay, let's have another look. Yeah.
Understand what's the velocity of magnitudes?
Velocity magnitude just means speed. So it's centimeters per year, like how fast it's moving. Yeah. Yeah. Okay. So a velocity is a vector. It's an azimuth and a magnitude, right? So what it's doing is deconstructing that velocity into the azimuth, the direction. So clockwise from north. And then it's just telling you the length of that vector, which is the speed. Okay, so that's the speed and the azimuth. The other things you mentioned is the angular velocity. That's of the plate, and it's more useful for other analysis. Like, for example, we look at like net rotation of plates. So you want to know the angular velocity. But for me, I don't really care. Like, it's not a very useful number for just knowing how fast something is moving. And then the colatitude stuff is more, again, some other numerical things that, yeah, you don't really need, or I've never used. Yeah.
Magnitude is moment magnitude.
No, it's magnitude just means speed. What's how fast is it moving? That's all it is. Yeah. Yeah. Great. Okay. Sure.
Why the value different is changing if we change the angle left, is it affect the coordinate system or?
Yeah, good question. Why do the numbers change if you change your anchor plate? So this is a really nice question, because what we're doing here, when I change the anchor plate to 802, I'm telling GPlates to keep Antarctica fixed in its present day position. So it's recomputing essentially the latitude longitude, which is, it's creating a motion path every 1 million years, assuming Antarctica is fixed, anchored.
The text is blue.
That's right.
Number is 0 compared to the other.
Yeah, so you're isolating just the Antarctic and Australian plate circuit. But if I change this anchor plate ID to B0, the spin axis, what this point inherits is the motion of Australia through Antarctica, Antarctica through Africa, and Africa relative to the base of the mantle. So it inherits what we call the absolute motion, not just the relative motion. Okay, so it's the total motion of this point in this mantle reference frame. Yeah, so the position is different because, again, it's the assumption of what's fixed or anchored. Your spin axis remains anchored, but then Africa is still moving, Antarctica is moving, Australia is moving. And so your point, Sabin's backyard in Sydney is now moving, with everything. But if you keep Antarctica only anchored, then it's just Australia moving with respect to Antarctica. Okay, so you're isolating that part of what we call the plate circuit. Okay, so let's just, I'm going to try to remember 30 degrees north, 80 degrees east. This is for India and Eurasia. So see how it's highlighted some of the times that the magnitude is greater than 15 centimeters per year. So it's just highlighting to you, you set that threshold before, and it might be highlighting to you, check whether this is plausible. Okay. And I think if I have the anchored plate ID to 0, you can see that it's speeds up. It's even a bit faster at times. So 16, 17, 18 centimeters per year.
So
Yeah.
put the longitude, and then plate ID. So we must know the locations that we put the coordinates.
Exactly. Yeah, exactly. And so, and this is all at the present day. So if you wanna track at, let's say, Siberia, okay. So if you want to say, okay, I want to track this point here in the middle of Siberia. So it's a latitude of 64 and 102 east. And because I've clicked on this area, it tells me its plate ID is 401. I can then go back to here, type in latitude 64, longitude 102, plate ID is 401, press enter, and now you have the motion of Siberia with respect to the anchored plate ID, which is the base of the mantle. Yes.
Is there any significance why we set a velocity warning, like yellow velocity warning, like velocity warning, etc.?
Yeah, so it's related to what is the speed limit of tectonic plates on Earth, right? I wrote a paper about this in my own PhD, and I think most people agree that there's some speed limits on influenced by the vigor of convection. So how viscous or not viscous is the mantle? Do you have a plate with lots of slab pull? Okay. And then do you have a plate with very large continents that have Archean keels that might be slowing down the plate? Okay. So just think of the plate as being dragged down. And if you have a big Archean craton that's sticking into the mantle, it will drag and resist that pull. So essentially what seems to be the case from the data that we have from the post-Pangea timeframe, tectonic plates that have no continental fragments and lots of subducting, plate length, like the Pacific plates, the Izanagi plate, for example, it can probably move up to 25 centimeters per year, right? 20 to 25. Yeah, there's no drag. There's nothing to really slow it down, right? And so maybe it's feasible that it could actually go up to 30 centimeters per year if you have some other, people talk about mantle plumes. As the mantle plume arrives at the base of the lithosphere, the head of the mantle plume spreads, and because it's so hot, it drops the viscosity of the asthenosphere, and it reduces the coupling between the plate, the lithosphere, and the mantle. So you can get lubrication and faster plate motions that way as well. But it still comes back to if your plate motion that you've implemented, that I've implemented, is more than 30 centimeters a year, you have to really think about why that is the case. It should be like a special circumstance that is supported by some kind of data at least, because it seems that there's some sort of physical limits on these speeds. Okay, but yeah, good questions. Okay, so let's start talking a little bit then about reference frames, because it's linked to this anchored plate ID concept. Okay. And maybe it's best if I bring up some slides on this, because otherwise I'm going to lose everyone waving my arms around. Okay, so we talked about the relative plate motions and small circles and fracture zones. But we want to now talk a little bit about reference frames. Of course, Sumatra can be your reference frame and say, okay, I'm just interested in what Kalimantan and the Java Sea is doing with respect to Sumatra, right? And very commonly what we do in tectonics and geodynamics is use the hotspots, right? So the hotspot at the present day here in the South Atlantic, the Tristan da Cunha hotspot is somewhere here. And we have all of these ocean island basalts, right, that have what we call an age progression. So the hotspot has burnt a hole through the lithosphere, and we can use that to reconstruct the absolute plate motions. But you then have to make an assumption. You assume either that your hotspots are fixed and not moving, that they're, vertical and like a candle, or perhaps your hotspots themselves in the mantle are also moving slightly. And so this is something we struggle with in geodynamics. So for example, the Indo-Atlantic hotspots, if you combine them all, they seem to be fairly stable. But if you bring in also the Pacific hotspots, they seem to be moving a lot more. And there's still debate why that's the case. Some people say it's the base of the plume is moving because a subducting slab is deflecting the plume. And maybe as well, the plume itself is being captured by a ridge. So as the seafloor spreading is happening and moving, the plume is being deflected. So anyway, but this is what we call a mantle reference frame. Okay, you isolate the plate mantle system. Okay, because your tectonics is all happening in the plate mantle system. Okay. However, there's a fairly important caveat, or a fairly important thing to remember. Who has heard of the process called true polar wander? Okay, it's a fairly niche thing that in geodynamics, but it's very important for us in our modeling. And the true polar wander is this idea that the whole mantle and the lithosphere move with respect to the core. Okay, because the outer core is a liquid metal at the present day. So it's a free boundary essentially. And the idea is that as slabs are sinking through the mantle, they change the moment of inertia of the plate mantle system. And the whole plate mantle system can decouple from the core. I'm sure you've seen those experiments and, kids' experiments where you spin on a chair and you bring in some weights and you spin faster or slower, right? It's the same process where you have heavy, dense slabs sinking through the mantle, and you essentially can speed up the motion of the whole lithosphere and the mantle together. Okay. So this is what we call true polar wander. The reason why that's really important is paleomagnetic data is actually capturing the true polar wander, right? So paleomagnetic data tells you only paleo latitude, and it tells you the position of your rock, your volcanic rock usually, with respect to the magnetic pole. And remember, the magnetic pole is, the magnetic field is sourced in the core, okay? It's not sourced in the mantle, right? So your rocks with the paleomagnetism actually capture this true polar wander signal. this is also important because if you have fossils or anything that's climatically sensitive, you need to be working practically in a paleomagnetic reference frame that includes true polar wonder. Okay. But for geodynamics, you want to actually remove and eliminate the true polar wonder because your mantle convection and plate tectonics only happens in the mantle and the lithosphere. So this is, something to keep in mind if you're dealing with any deep time reconstruction that's climatically sensitive, that's using paleomag data. It needs to be in a paleomagnetic reference frame. If you're looking at, mantle plumes and the plate mantle system, you should be working in a mantle reference frame. Okay. Now, in GPlates, like in this model that I have, so if I reconstruct to 100 million years ago, Bandung here is at 1.85 degrees north, okay, in the mantle reference frame. If I now switch to a paleomagnetic reference frame, which has its own special plate ID in this case, which is 701, 701, you can see that things shift. In this case, it didn't shift much latitudinally. It shifted by maybe 3 or 5 degrees. Okay, so it's now 3 degrees south. If I go to just 55 million years ago, and I look at, this is quite recent, this is the Eocene, right? So the southern tip of South Africa is 50 degrees south in paleomag. If I switch back to a mantle frame, it's about 40 degrees south. So the paleoclimatic, impact could be pretty significant of a 10-degree latitudinal shift, even at fairly young times. Okay. So, it's worth kind of keeping these things in mind. When you're thinking about plate speeds, convergence rates, again, you want to be working in the mantle frame, which in this case is an anchored plate ID of 0. And so you can actually see, hang on, let me just move my zoom windows. So in the mantle frame, you can actually see better the seafloor spreading history in the Atlantic. But if I change that back now to 701, 701, it's a bit harder to see because it includes some of that true polar wonder. So most people don't really care about this at all, right? And I understand it's a technical thing, but I've seen too many papers and studies use the wrong reference frame, and it could mean that the whole study is completely scientifically unsound. Okay, I've seen people look at, for example, the latitudinal diversity of plants and animals, right? But they're using a mantle reference frame, and that, like, by definition, is an incorrect use of the plate reconstructions. Equally, if you want to run a mantle convection model, and I've seen this, people using a paleomagnetic reference frame, that's wrong too, because you're combining the velocities on the surface with also the traction of true polar wonder, and you're getting the wrong, boundary conditions. So this is more for you to remember in case you ever have to work with climatically sensitive things or plate mantle system stuff. Okay, great. Any questions on that? Yep.
Yeah.
Usually we work respectively to the Sunda block as a anchor. What do you suggest for this?
Yeah, from my experience, Sumatra is probably the
Maybe in Malaysia?
yeah. So let's just go to the present. It's completely up to you, right? Like you can use, Kalimantan, the core of Borneo, as your anchor. The issue I've seen is that there's a lot of oroclinal bending here. If you look at the geophysics, the gravity anomalies, and the paleomagnetic data, it looks like there's been quite a lot of counterclockwise rotation of Kalimantan in the Cenozoic. Probably in response to Australia colliding here to the east, but also India colliding to the west. So the whole Sundaland is being, deformed and bent. So whatever you're more comfortable with, whatever makes more sense. Yes. Yeah. Yeah. So do you mean like this part? Yeah. Yeah. So the reference, the anchored plate ID I'm using in this case is just Sumatra, the 673. You can look at Kalimantan, right? You can say that's 614. We can change that to 614. And so let me play that back. And so you'll see that rotation with respect to Kalimantan. Okay. And this could be completely wrong. This is what I think your students will fix the mess I've created. But that's how we can, isolate these things. Now, just remember though that GPlates will happily recompute the positions in a different reference frame. One thing you want to be careful with, particularly when you're in deep time, there may be paleomagnetic constraints that say, well, Kalimantan has to be in these certain latitudes. Now, of course, paleomagnetic data has its uncertainties in age and in latitudes, right? It's like often 10 degrees, in latitude uncertainty at best. But for example, like even in the Jurassic, I forget the exact age. Let's have a look. So let's see, what was it? I think it was like 150 or something. I think around 150, it's meant to be Kalimantan. There is some paleomagnetic data that says it should be near the equator. So here it's at like 5 degrees north, and that's probably within the uncertainty of paleomagnetic data, right? But if your model is telling you that Kalimantan is on the Gondwana margin at this time, then that's 42 degrees south. And so therefore it's probably not the right answer, right? You want to try to minimize the, disagreements between the data sets. Okay, any other questions? Great. Okay, so let's switch gears a little bit and talk about some of these big advancements that GPlates allowed, which is the plate tectonic evolution itself, right? Like we can move terrains around, but to extract the velocities and the area of the tectonic plate, we need to think about the plate boundaries themselves, okay? Because, the definition of plate tectonics is you have an interlocking network of plate boundaries, The reason this is really important is without the plate boundaries, so if I turn them off and turn this off, I can move the terrains in any which way I want. I can make the terrain spin around, and if you create a figure for a paper, it might actually even look feasible. But if you actually look at the plate driving forces, it might not work. Okay, so it's about moving terrains, but moving them on a plate, a tectonic plate that is like a conveyor belt, right? Because that's essentially what plate tectonics is. So what we have in GPlates is this ability. So if I just, you can follow along. So, we can just have the topography. We can activate the feature geometries and the plate boundaries. And so to actually see the feature geometries, you can see that I turn it on and off, nothing happens. And that is actually hidden in this menu under View and Geometry Visibility. So this is a useful little menu as well. You can hide all certain, types of geometries. So you can hide all the rasters in one go, right? I can bring them back. But here we want to show the topological sections. And then you see a mess of lines. Did that work for everyone? So View, Geometry Visibility, and Show Topological Sections. Did everyone manage to show their topology, feature geometry lines and points? All right. So what we can do now is I can just demonstrate to you what's actually happening. What GPlates does in reconstructing plates and the topologies, and this is one of the key things we need in plate tectonics, is it reconstructs every single plate boundary individually first. Okay, so this mid-ocean ridge is the South Atlantic ridge. It actually has ridges have a special behavior because they move in between two plates. This is what we call half-stage rotations. Okay, and so that's why they have a left and right plate ID. So 701 being Africa and 201 being South America. Okay, so you have a line that's moving, okay, in that way. You then have another boundary on this side, which is a subduction zone, and the subduction zone is fixed to what we call the overriding plate, the upper plate, okay? And so this is South America, and it has a plate ID of 201. You then have some other, fracture zones, transforms, and whatnot. So if I can now, if I anchor 201, South America, you can essentially see how this network of plate boundaries changes. So what we do is we create those individual boundaries, and then we tell GPlates, okay, these lines participate in the topology. GPlates then reconstructs them, intersects them all, and creates what we call an evolving topology from the intersection of those lines. So do you see now I've clicked on I've selected the ridge. In this bottom panel, you can see two plates, adjacent plates, the African plate and the South American plate. South American plate is given that plate ID of 201. And if I reconstruct, you should be able to see that this line, the mid-ocean ridge, is moving slowly away from South America. Let's have a look at some other examples. I can anchor India. You can see that these lines are all moving independently to each other. Okay. And then we have the tectonic plate, this resolved topology, where all of these plate boundaries are intersecting. Okay. This is what allows GPlates to actually sample the velocities, right? This is the whole point. Like, this was the big advance of not just being able to track the terrains, the little polygons, but actually track the entire plate and its boundary evolution. This is very useful for us because based on this, we can calculate the seafloor production rates, seafloor spreading rates. We can calculate what is the subduction rate, what's the subduction flux at the Java Sunda Trench through time. Maybe that has some correspondence to the volcanism and volcanic history along the margin, because you can imagine the more slab you're subducting, the more volatiles like water are being released. Maybe there's more volcanism as a result. So tomorrow I'll show you the process of actually editing and incorporating these topologies. Okay, because that's quite an advanced feature. I just want everyone to kind of be comfortable with some of the fundamental concepts today. Okay, does that generally make sense how these topologies work in GPlates? Great. Okay. Let's do some more fun things now. I took you into the deep end and we talked about true polar wonder and plate topologies. So let's do something a bit more fun. Let's talk about rasters, because I think that's actually quite useful to many of you, because you can bring in your own rasters. And I can show you how rasters work in GPlates. When you download GPlates, in most cases, you get a geodata folder in your program files. So let me show you what it looks like. It looks like something like this. And there's a folder called Rasters. And these are sample rasters, gravity anomalies, crustal strain rate, crust thickness, free air gravity, global geology, magnetics, seafloor age, lots of things. Okay. Again, because I'm not able to bundle very large files, the resolution is still fairly limited here. Okay. But you can see that in this case, the raster is of global extent, and that makes it very easy to import into GPlates because it's just a PNG or a JPEG. It's, easy to import these global things. So I'll show you how we do that. We go to File, Import, and then Import Raster. We then point it to the raster file in this. Global Geology PNG. We click Continue. you're able to load in a regional raster. Okay, so I don't think it's showing up yet. It's a bit delayed on Zoom. So I'll just wait for it to catch up. Okay, so online you should be caught up now, but we can specify the extent of the raster because it's just a JPEG and PNG, it doesn't carry any georeferencing information. In this case, it's global, so it's all fine. I click continue and done. Okay. So you get a nice UNESCO global geology. The problem is you can now reconstruct, but you can see that the raster isn't moving. Okay. But the good thing is the GPlates makes this process very, very easy. Okay. So we go back. This is good. We're using our skills from this morning. We go to Window and Show Layers. Okay. You'll notice that there is a new layer now here called Global Geology. You can click on the little arrow and expand that layer. What we can now do is connect that raster to any polygon layer, right? And GPlates will cookie cut it and move it with those polygons. And remember at the beginning this morning, I was telling you about how important this static plate polygon file is because it covers the whole world in these polygons. So I can go here under reconstructed polygons, add a new connection and put in the connection to the static plate polygons. And at present day, nothing happens, okay? But now if I reconstruct, look at that. Okay, you can see how quickly GPlates, did the cookie cutting and reconstruction. And remember, you can now easily export that raster as a GeoTIFF. Okay, so I can show you what I've just done, following the steps from this morning. Oops, that's the topography. It's not what I want. Okay, so I exported and outputted the global geology in the paleo coordinates as a GeoTIFF. Okay. Okay, I'm going to show you something. I couldn't pack up this package this very large topography grid, but I'll show you how this works as well. Where is my topography? Here we go. Okay, so who has ever worked with IMG rasters in ArcGIS? So it's just a numerical raster file of topography at the present day. So I can do the same thing. I can go File, Import Raster, point it to that file, press Open. This will take maybe even a few minutes to load for the first time because it's a very large, high-resolution raster. But I think it's worthwhile doing it. There it is. Okay. I click on Continue, But do you notice that it didn't ask for the extent? Because it doesn't need it. It's reading the extent from the georeference information inside the raster. Okay, I click done, and I have a very high resolution topography. I mean, it's not that high resolution, but you can get high resolution. You can bring in LiDAR if you really got very excited. But yeah, you just it would need to be a raster first, so you have to convert it to a GeoTIFF or something like that. Yeah. Okay. So again, we have the same problem that it doesn't move. And again, it's nice for me able to demonstrate this again. I expand the layer, add a new connection under reconstructed polygons to static plate polygons. And you can see how efficient GPlates is with this process. It's like a 1 gigabyte raster file, and it's happily, reconstructed it quite quickly. Because this is what we call a numerical raster, you can actually change the coloring directly in GPlates. So if you've expanded the layer, you can click on this button that says choose built-in palette, and you can change the color palette in here. You can remap that range here. Okay. Oh, it hasn't caught up. Sorry. Let's just wait for it to catch up. Okay, so this is the raster we saw this morning. And this is what happens when I turn on the high resolution numerical raster. Do you see the difference in the resolution? Yeah. Great. There's some other more advanced features you can add. For example, you can add this thing called a relief raster that highlights shading, sun shading. You can actually just connect it to itself as well. Oops, that is not what I wanted. So you see a bit more of the fabric of the raster. You can, for example, in this case, also attach gravity anomalies and shade by the gravity anomalies as well. So you can emphasize some of these features more. So I'm going to get you to follow along for this next one, which is to bring in the seafloor age grid. Yes? No, there isn't, because it was going to be too big. Yeah. I can share. I can definitely share them with you, but it was the original zip file I made for you guys was 33 gigabytes big, and I'm like, this is going to take people a while to download. So sorry, but yeah, these are the public grids. I mean, I can, if you need any, just send me a shopping list, and I'll send you back the full size files. Okay. So can you folks try to find your GPlates geodata? So if most of you are in on a Windows, go to Program Files, GPlates, and then see if there's a geodata folder. Because I'm curious, for some people, they don't have write access to the program files folders, and it can cause problems. So I want to check with you. Yep, beautiful. So stay there. Oh, you don't have program files because you're on a Mac like me. So let's go applications on the left. And you have, yeah, so go inside there. I'm not sure. I always forget. Try the top one. And then, okay, so there's no GPlates here. So maybe it's in the other one. So go back, sorry, and do this one. Yep. And then, is there GPlates here? Here's GPlates installed then. Oh. Okay. Can you search for GPlates, a folder or something like that? Is it moving?
No, yeah, it's not moving.
It's not moving. Okay, so here what we need to do is under global geology, you expand it and then add a connection to reconstructed polygons. To see this present day static polygons. And nothing happened because I think you have multiple layers loaded. You have multiple versions. That's okay. We just go connect it. Yeah. Great. Great. How did you go? Did it work? No, it's not moving. Is it moving? No. Okay. So global geology, expand, and then add a connection to the static plate polygons. Yep. So now it moves. Great.
Which folder that contains Etho4
So the Rasters folder,
folder on your
but it doesn't have the high resolution one. So I'm going to demonstrate to you now the seafloor age. So just stay on this folder. Yeah. Yeah. How did you go? Yeah, good. You've got the data. That's good. But let's see, can we find the geodata, the GPlates one? Can we go to your C drive?
This checking is not there.
Okay. Yeah, yeah, it could be. Yeah.
Well,
So C.
yeah, it's too big, so much.
That's okay. So we go program files x86. Yep. It looks like there's no GPlates here. Can we go back? Okay. Yeah. Can we go back and then try just this big one up the top?
Oh yeah.
Yeah, GPlates. So can we open it? And then this one, and then geodata. Yeah. Okay, beautiful. Excellent. Question. Okay. There's a question related to
No,
Flores.
yeah, correct.
Yeah. I think it's to do, there's a velocity artifact there. Well, let's have a look. What age does it happen? It happens at 65, so let's have a look. And I suspect it's to do with the fact that like the island of Flores in this model is not even captured to go back that far. So let's go. So it's 652. And see, it's got this valid time of 9. Oh, ooh, sorry, that just jumped. So it only appears 9 million years ago in this model. I don't know, how old is Flores meant to be? Do you guys know? I mean, I can make it much older and we'll be able to see the artifact, and we can see, like, let's make it appear at 100 million years. Yeah, see, like it starts moving. It's like a ghost. It's moving in a different direction. So the reason you're seeing that problem, so let's go to 65. Yeah, see how it jumps? That's the velocity artifact, but we don't see it because in our model, the island only appears in the last 9 million years. And that could be wrong, but at least it's consistent, that like it's just hidden and it's not being considered. Yeah. Okay, great. So what was that? Oh yeah, I wanted you folks to bring in a numerical raster from the geodata bundle. So the geodata bundle is different to what I sent you. Okay, I sent you a special bundle that is good for training. It shows you how to bring in raw data and things. The geodata bundle is what we also ship with GPlates. It also can't be too big because the programmers get angry at me. But it's got an example here of a numerical seafloor age grid. So let's have a look at this. It should live in rasters and then seafloor age grid. Has anyone managed to find that? Okay. So in this folder, you have a project file, which we're going to ignore for now. We have a GPML file and we have a netcdf grid itself. Okay. Now, anytime you import a raster into GPlates, it creates this GPML file that you can use easily next time. So you don't always have to do that import step. Okay. So in this case, for example, I can just drag and drop and it will create the raster. You noticed as well, it created 2 files here called GPlates cache files, and that's helpful for the rendering for the graphics engine, okay? You can delete them after you're done using these. They will regenerate on their own. One thing I'm not sure about in your case is that at some stage in the last few years, Windows has locked down write access in the program files folders. So if this doesn't work and if it crashes your computer, please tell me, because we're going to have to think about packaging this geodata separately from GPlates. So has anyone managed to drag and drop it? Or if it doesn't work, you can go to File, not Project, but Open Feature Collection. Okay. So you should get something like this. Has anyone managed to put your hand up if you've managed to get something like this? Yeah, most people. Yes. So the GPML folder, the GPML file is still in the same folder as the netcdf grid. I can show you what happens if I just, oops, yeah, I just deleted them. I can eject. So if I do that step before of importing, so go File, Import Raster, I specify the raster, and because it doesn't have the GPML file in there, it will now ask me a few extra things to generate that GPML file. Okay, so it says, yes, read band 1, sure. It doesn't need a geographic extent because it's reading that from the numerical grid. And then you can see that it's generated a GPML file and the cache files. And I'll just demonstrate that again, that if I delete the cache files, if I drag and drop the GPML, it regenerates the cache files, and I can see the raster. And this is a raster of seafloor age. And if we expand that, bless you, we can change the built-in color palettes. So for example, like for the seafloor age grids, you can play around and try one of these color palettes. Similarly, you can remap the range, narrow the range if you're interested in, very young ages. You can see the seafloor here. And again, just like before, you can connect reconstructed polygons, this layer, which is the static plate polygons. Okay. Okay, how's everyone? Managed to load up the seafloor raster. Okay, it didn't crash. It seems like we might on y-axis program file. You expand it. Different little black arrow. Go down. Choose the D that will color palette changes responses. Okay. You can go to check, it just looks the color. Right. You left, blue, black. Trying to go down and then we change the color. You can select one of these, and you'll see a drop change. Yeah. Okay, great. So I'm just going to demonstrate, and you don't have to follow along to this step. I'm just going to demonstrate the I'm going to demonstrate how we reconstruct the numerical rasters. Okay, so just like before, reconstruction export, we can just do at one time step, 50, 50. Instead here, I'm choosing the export type as a numerical raster. And for QGIS, ArcGIS, we can just use GeoTIFFs. You can change the resolution if you want, higher or lower resolution. Click OK and export. And so let's have a look what happens. Okay, so this is the topography, present day topography reconstructed to 15 million years ago. And you can see that rather than being red, green, blue, colors, it's actually a numerical value. And so it means that you can recolor. You can recolor in QGIS, ArcGIS, this numerical raster. Okay, that's the difference. And you can see it's done the same thing for the seafloor age grid. And yeah, so you can do more coloring, more symbology again, externally to GPlates. It will export anything that you've got visible, but it will export it to separate files. Yeah. Yeah. Great. Okay. The last thing I wanted to show with the rasters is, let me find my files. I'll just walk around and see if there's some questions.
I want that. Yeah, because I don't.
Yes.
Oh, this is.
Yeah, you can import GRD. Be careful though with GRD files. GRD files, like the extension is kind of non-specific. There's arc info GRD files, but there's GMT GRD files as well. So, you know, sometimes it might not work. But it should, look, it's designed that it uses what we call the GDAL engine. And GDAL easily deals with lots of different geospatial file types, different rasters, different, you know, geometry files. Okay, great. Okay. Amazing. Okay. So we've got about 30 minutes left today. So I think what we'll cover is what we call time-dependent rasters. And then we'll cover the 3D volume visualization because it's actually quite relevant to the time-dependent rasters. And that way, tomorrow morning, we can spend a bit more time on other things. So let me just update this. Time-dependent rasters. Oops. Great. Okay. Time-dependent rasters. GPlates can display rasters at different times in the reconstruction. Okay. So it could be changing precipitation in the atmosphere. It could be changing what we call dynamic topography from mantle convection. And in this case, what I've done is taken a global tomography model and used some very simple comparison because we know in geodynamics that slabs don't sink only vertically and a constant rate everywhere in the world. So it's just a very, basic thing. The reason why it's important to demonstrate as a time-dependent raster is that you can see in the file name right at the end, there's a number, and that represents the age when it should be displayed. Okay, so if your GPlates is reconstructed at 20 million years ago, it will read this file. You can, in this case, do two things. You can do import and then import time-dependent raster, or, oops, or just use the pre-existing GPML file and drag and drop it. So you can drag and drop it, and I'm going to just also demonstrate what happens if you don't have a GPML file. Okay, so I would go to File, Import time-dependent raster. I can add files. I can select the files I'm interested in. And as I mentioned before, it has to create these cache files. And before it creates the GPML, it just checks in with me. It's like, yes, I've read the time from the file name. And your anchored plate ID should be back to 0 in So just drag, drop, and it will generate the cache files over a couple of minutes. Let's just check that it's, beautiful. Excellent.
With the number on it doesn't matter the one for.
Exactly. It only reads the last number that's separated by an underscore or a dash. It just reads the last thing. Deep, well, yeah, that's a good question. What is deep time? It just means like millions of years, like really old. Yeah. How'd you go? So you're back in geodata and you're going to the time-dependent rasters and loading in the tomography, which is great. You've got it here, good. So go to the bottom and just load in. So go to the bottom and we actually don't want to add them. Go cancel and let's cancel this. You just want to add the GPML file that exists already. So you can either drag it or go File, Open file, Feature Collection, yep. Go to that folder, Geodata folder. Rasters, yep, beautiful. And then time-dependent rasters. Yep. And then, yep, that one. Beautiful. Okay. So if we have a look at this, if we zoom in, what we should expect is that, Sunderland is in the vicinity of some blue material, which is your subducted slabs through time. This can be quite helpful to see, okay, well, where is the subduction? I always find it quite telling and interesting that the northern arm of Sulawesi looks like it's imprinted in the tomography, even going, quite far back in time. So it seems to suggest to me that maybe the northern arm of Sulawesi is, Carthaginian from, Sunderland, whereas the Sula spur is more of, the Gondwana affinity. But that's kind of what the tomography might suggest. Okay, so that's the time-dependent rasters. All good? The next thing I want to show you is how to do 3D volume visualizations of this same tomographic model. Okay, we want to be able to, visualize anything that you might have in the mantle. It could be a regional tomography model for your area. It could be a global tomography model. It could be, other things as well. It could be a geodynamic model output. So let's have a look. If we go to the geodata, let me see. Yep, it's under this folder called Scalar Fields. And I can, again, click and drag and drop the GPML file onto the GPlates window. And nothing happens because there's a lot of rasters covering things. So now you see the tomography model. Okay, so we're going to play around with that a little bit, but let me just hide a few layers so it's a bit easier to see. Has everyone managed to open it up? So you can go to File, Open Feature Collection, and then go to the geodata, and it's Scalar Fields, and it's the MIT P-Wave tomography model. And in this case, just to keep the thing manageable, I've cut out Southeast Asia, or part of Southeast Asia. But if you need the global model, let me know. I've got those files too. Okay. Okay, has everyone managed to load up the tomography model? And just a reminder, you might have a lot of things covering it. Okay, so you might have to disable or, sorry, hide the raster layers because it's right at the bottom here as one of these blue layers. That's the tomography. I've somehow managed to load it twice. So, okay, I'll walk around and just check that everyone's comfortable with that. So geodata, scalar fields, the MIT. Yep, so we'll go definitely into all of that. Oh, it shows black. Oh, that's exciting. Why is it? Oh, sorry, I just realized. Okay. Okay, so we definitely, what I think we need to try is file, open feature collection, and then do that. And it's really interesting on your machine, it just is opening it as a layer rather than a 3D volume. So I think there's an issue with a graphics driver here, actually. Yeah, okay. What about you? Did it work for you? Okay. Yep. So open files, yeah. Yeah, you're having the same issue. Yeah, is there any errors? No, nothing too obvious. Yeah, this looks like a graphics card issue. Okay. Most people seem to have gotten it to work. Good. Okay. All right. Great. Let's talk about so unfortunately for a few people, it looks like it didn't quite work. So for two people, it looks like it's read in as a raster, but it should definitely be a 3D volume. Okay. So I'm going to demonstrate to you what we can do with this. Okay. So one of the first things when we expand this layer, at the very bottom, there is this thing called sampling rate. So you can actually, to get a bit more detail, you can make that 210. That just makes it a bit more crisp. You can play around with this depth restriction. So you can see that it's going from a radius of 0.55, which is the core mantle boundary, all the way towards the surface. So you can look at slices, the depth slices into these things. There was a really good question here about the units. So these units in most tomography models is the delta, it's the difference in the seismic velocity or the seismic velocity anomaly. 0 being ambient mantle, positive velocity anomaly is like a slab. So positive, a faster velocity is a slab, and a slower velocity or negative number is something hotter, right? So it's slower. The seismic wave is going more slowly through that hotter region. So you have a few options to color by the depth, gradient, and so on. The key thing is to look at this ISO value. So you can play around with the numbers, put in like 0.3. It's a positive number, so this will highlight the slabs. So this highlights the Java Sunda slab. And you can see that perhaps there's some kind of break in that slab at this place. You know, if you have very high resolution tomography, you'd be able to even probably see the Toba, you know, magma chamber system sort of thing as well. Okay, you can click on this option, which is the double deviation window, and you can put in the negative ISO values, and this will show you the hot stuff. Okay, this is, yeah, you can play around with this visualization. So let's actually, I'm just going to stick to the single deviation window and change the contour. Oops. So what this is showing is the upwelling hotter material. The blue areas represent that you're looking inside the volume. So the coloring here is a little confusing sometimes. But essentially what you should be able to see from here is that you're highlighting the mantle wedge, but you're also highlighting this interesting area of the South China Sea. There is a plume here called the Hainan plume. So it's a hotter part of the mantle. And you can look at, you know, I guess the details of like, well, you know, where are the upwellings, where are the downwellings? So if I try then, let's look at slabs again. You can start to kind of make sense of the depths and the slab dips and whatnot. The last thing I wanted to show today and related to this is how you can digitize a line in GPlates and how you can use it to create a cross-section through any of these 3D volumes. It could be, yeah, as I mentioned, tomography or geodynamic model. And just more generally, how you can digitize things in GPlates, right? So this morning we used the view tool, then we learned about the feature inspection tool. Now we're going to activate the digitization tool. And I guess conforming with, I guess, shapefiles and so on, you get an option to digitize a polyline, point or multi-point, and polygon features. For our purposes, let's just stick to polyline. And then, just like in QGIS and ArcGIS, you can start by clicking points and you'll get a particular geometry, okay? So I'll demonstrate this a few times, but to go to the next step, I can create this as a feature. I can select a feature type. I don't really care at this stage. I can give it a plate ID. Since it runs through Kalimantan, we all remember, what was the plate ID? Who remembers all the plate IDs yet? 614. 614. We can make it begin in the distant past, so it's always going to be there. I can click next, next. And I actually want to show you how to create a new feature collection or a new geometry. And I want to show you how we can save that as a shapefile or a GPML or both. Okay. So I'm creating a new feature collection and I can click on this create and save. This, I'm going to show you this a few times, so don't maybe just watch it first to follow along. But it brings up the Manage Feature Collections window, and it has this orange layer now, which is this new feature collection I've created. I can click on this Save As button, and then put it in, you know, somewhere where I've got my project. Doesn't really matter. You can put it in subfolders, and we can just call this a cross section. you have the option to save it as a GPML. You can save it as a shapefile. You can save it as a GMT file, a GeoJSON, lots of things. So let's save it first as a GPML file. But you can also go back to File, Manage Feature Collections, and any of these geometry files you can do Save As, and you can save them as shapefiles as well. Okay, so that's very easy, I think. Okay, so maybe I can just demonstrate that again. I've activated the digitization tool. I've activated the polyline digitization. I've just started digitizing something. I create a feature. If I've made a mistake, I can just clear geometry and start again. Create feature. In this case, unclassified feature is okay. Again, plate ID. You can put in a name if you want. Distant past is what you prefer here. Click next, next. And then in this case, you can add it to an existing layer, or you can create a new feature collection separately. Okay, so we can just, maybe just for demonstration, I can just put it in the existing feature layer. So what I'm going to do now is show you how we can use these lines to visualize as a cross-section through the tomography. Under this cross-sections thing here, I can connect this new layer that I've digitized, and I can, in the render mode, choose cross-section. I can delete one of these. So I can show you how we can delete features because I've got too many things here. Again, select the line and then delete. One of the really cool things I can do here, well, before I do that, let's actually look at the color palette now. I just want to make sure that the color palette makes sense. So positive numbers should be blue and negative numbers should be red, right? That's the seismic velocity anomalies. So if I choose built-in color palettes, I can click this button at the bottom that says invert or flip the color scale. And no, that's not what I wanted. So you just choose an appropriate color scale that you can see. So blue means fast, positive numbers, and red means negative or slow seismic velocities, which is the hot stuff. The cool thing that you can do with GPlates is you can very easily edit geometries. So if you select a geometry like this line, I can click on, add vertex. I can delete. And then what I love, which is really fun, is just move the vertices very easily and be able to see, quite, live what's actually happening to the tomographic cross-section. Okay. The only problem, which I've requested many times this feature, is to be able to tilt the camera view so I can look at this slice side on. Unfortunately, that doesn't exist, but you can play around with that. And I should be able to, export this as a projected geometry, scalable vector graphic, and preserve, the tomography here. So let's just see. Where am I? I have too many folders. It's going to take a little while to load up Adobe Illustrator. That's fine. But has anyone had any problems digitizing a line and creating a cross section? Because there was a few steps involved there. Yeah. Yeah, I can repeat the whole. Yeah, that absolutely. Great. Excellent. So let's do it together. Okay. So let's do this step by step together. So let's activate the digitization tool and click on the polyline. Okay. Everyone happy with that? Excellent. Let's start digitizing a cross section that goes from south to north or north to south. It doesn't matter. So left click the first point and keep clicking to create some sort of line. It doesn't have to be straight. It doesn't, doesn't matter. Okay. So have we got something like that? Excellent. So when we have that, we can create that as a feature. Yeah. Create feature at the bottom right here. For this purpose, we can just say unclassified feature. That's all fine. Click next. Plate ID. We remember all the plate IDs, 614 being Kalimantan. And click this begin time to be distant past. Yeah. Have you got something like that? You guys in the back have very good eyesight. I can say that.
548. That I don't Java.
Yeah.
Java and
Good question. I'll show you in a moment. Thank you for reminding me. So we've put in the plate ID. We've said distant past. We can change the plate ID, so that's all fine. We can click next, ignore this. And then here you can choose to add it to an existing layer or create a new feature collection. So I can create a new feature collection and click create and save. And it will come up with a window like this. So this new feature collection you can save as, and you can call it cross section.
New feature collection and then.
Yep. Save as. Oops. Save as. Cross section. You can call it whatever you want. Maybe for now, just save it as a GPML. And then save. And it will now have saved that to your disk. Remember that you will then need to save the project as well. Say separately, say project as. If you want this to remember all the different links and files and whatnot. Okay, has everyone managed to get a line that looks like something like this? Yeah. Great. So in the layers window, if you scroll to the bottom where your tomography thing is, MITP regional, okay, you can add a new connection under cross sections. And then you also change the render mode to cross section. So first, So first you need to add the connection. So let's do this together.
Intersection.
Add new connection to cross sections. And that's the new cross section. And then just make sure this button is clicked as cross section. That is the rendering mode. Did you get it? Excellent. And then you can muck around with the color palettes to you know, specify the color palette. You can select the line. When it's white, you can move the vertices and see the tomography very quickly and easily. And as I mentioned, you can then export this into, you know, Inkscape. You can annotate this. You can use this probably in a figure already, you know, for a paper or presentation or something.
To edit the line.
Yep. To edit the line is you go back to the select. Select. So you click on it to make it white. Yeah. Click on it. Click on the line. Yeah. And then you can add points, delete points. You can cut the line or you can move the vertex. Oh no. We broke GPlates. Yep. Yep. Yeah, let's have a look. I think it's because this is open.
Oh, close it.
Yeah, close that. Yeah. So now, yeah, select a vertex and move it. Oh, okay, let me see. What's going on?
Oh, this one.
It's just, I think the points are very small.
Oh. Okay.
Yeah, it's very, on Windows, the points are very, very small. So it can be hard. But yeah, it definitely works. Good.
Sorry,
Yes. Oh, great. Look at that.
for this unit, we use the ISO value to
Yes.
filter it, right? For the same value as the section make, but what is the spell as about? I think it's like the height of the mantle, or
Yes, exactly. So it's what this is a tomography model. It's a P-wave global tomography model. Yeah, and so it's just highlighting areas where the velocities are fast. The seismic velocities are fast is in here your red colors, and slow is your white colors. So, but a basic interpretation of that is fast seismic velocity anomaly means a subducted or colder mantle.
also it determines the velocity and P waves of the.
Exactly. The temperature changes the density of the mantle somewhat. So where it's hotter, it's less dense, and the seismic velocity slow down in it. The P waves slow down. Yeah. Great. Good questions. Great questions. Okay. That's it. You've graduated. You're done. You can now publish with this stuff. All right. Well done. Thank you for today. We managed to cover quite a lot of ground today. Tomorrow let's just go. Sorry, I have to go back to my slide here. So tomorrow we can talk about importing your own data. So if you wanted to bring in any of your own data, like any geochronology, whatever, geochemistry, I have for the demonstration, I just have fossils from the paleobiology database. I'll show you then how you can assign those plate IDs to your point data or whatever, vector data. We can talk a little bit about the Python API, talk a little bit about the theory, and then get into the really advanced things of looking at the deforming model, and then also being able to modify the position of things, modify the plate boundaries. So they're like kind of the very advanced user expert level things. And I normally don't have the time to cover these things in workshops, but since some of you are very generous with your time, you're now stuck with me, and we can go through some of the advanced things. And then we can add an end on some broader things on paleogeography, paleoclimate, paleoprecipitation aspects. And yeah, throughout all of it, Q&A if you've got some questions. Does that sound okay? R. Okay, we can have a look at the R plugin, just at least the basics, because I haven't worked with the R plugin myself, but I've helped Adam Kochis in terms of developing an R plugin with GPlates. And there's a few ways of using R with GPlates. There's an online web interface, but there's also like a local version where you can run GPlates from the command line with R, but we can have a look at that. Okay, well done, team. See you tomorrow.